This was due to unforeseen and surprising technical problems with PDF LaTeX. And you'll see the results of those problems still there, but I'll try to do my best to go around them for you. So last time, we stopped at nonparametric clustering based on kernel density, based on density estimation. And what we saw, and we'll come back to that at the end of the nonparametric clustering chapter, is that for these methods, there is no cost function to optimize. However, they seem reasonable. And so nobody asked me yesterday, where is the cost function to optimize? That's one criterion that shows that they do seem reasonable, after all. Today, we'll talk about another probabilistic-based method, and that's Dirichlet process mixtures, which, interestingly enough, has also no cost function to optimize, or it's not exactly optimizing its cost function, but which nevertheless is based on a probability model. And this is the Dirichlet process mixture model. I will start with an aside, which is the Dirichlet distribution, which is sort of in a more convoluted way related to Dirichlet processes. How many of you have actually encountered the Dirichlet distribution already? Some, more than some. So the interesting thing about the Dirichlet distribution is that it is a distribution over distributions. And that's what makes it a good preamble to Dirichlet process mixtures. So we start with a discrete random variable that takes R values. And we denote its probability distribution by P sub z. The random variable is z. And the parameters of this distribution are theta. Theta j is a vector of parameters that sums to 1 is positive. So the domain of theta j is the probability simplex of all the distributions that, all the thetas that sum to 1 and are not negative. Also, you probably know that if I want to compute the probability of a sample of capital N draws from this distribution over z, the probability of the sample is given by this expression, which basically counts how many times value j appears in the sample and takes theta j to that power. Again, this is very simple. It's called the this is not strictly the multinomial distribution. The multinomial distribution will have some coefficient, but that's just the probability of a sample. And the n1 to r, the counts, are called the sufficient statistics of the data. And I expect that for most of you, this is already well-known stuff. Now we get to the Dirichlet distribution, which is a distribution over the domain of theta. So it's a distribution over distributions of the form Pz. And this is defined in the following way. This is the domain. This is the variable theta. And the n primes are parameters. So it depends on r parameters. What's here is a normalization constant, where gamma is just the gamma function, the generalization of the factorial. And here is the distribution itself, the dependence on theta. So it's a product of the parameters taken to the powers n prime j minus 1. And minus 1 comes from the fact that here there is a minus 1. So the reasons of integration, let's say. Yeah. This is the Dirichlet distribution. It's called often it's called the Dirichlet prior, because distributions over distributions are often priors for estimation of the parameters theta. What is interesting about it, about the distribution, is the following. First of all, the thetas appear in a product form. However, it's important to note that this is not a distribution where the thetas are independent. Can you see why is that? Yes. So the thetas are constrained to sum to 1. So there is a hidden constraint that the domain is not a product of intervals, that the thetas are not free. They have to sum to 1, and they are defined in the simplex. In fact, I would like to show you how it looks. suppose we have R equals 3, and therefore, this is the probability simplex. So this is the set of thetas that sum to 1 over distributions over 3 items. And the Dirichlet distribution is defined over this domain. Yes. It has a peak, and the peak, I think you probably guessed what it is. The peak is at the place where these n primes, it's at a probability that's proportional to the n primes. So supposing that n prime 1 is equal to n prime 2 is equal to n prime 3 and is equal to 5, the peak is here in the middle. Yes. And the distribution decreases. This would be the level curves towards the border. Okay. That is the reason why I denote the parameters with n prime, because they act like sufficient statistics for the fictitious distribution that is the peak of this Dirichlet. Yeah. So there is a distribution here which has theta star 1 as n prime 1 over sum of the n prime j's, yes, which is 5 over 15 in this case. By the way, can you see? It's kind of it's kind. All right.
Sorry about that.
The managers have stepped in.
There we go.
There I go. OK. Well, OK, I'll try to.
See if it works better.
So, test. Can you see it?
There we go.
Theta. All right. From now on. So, can you still see this? So this is the peak of the distribution. This is the peak of the distribution. There is a significance to the sum of the n primes. The sum of the n primes gives me the strength. So if I multiply this with a constant, I get the distribution to be more concentrated around its mean. And if I multiply them with a constant at below 1, I get the distribution to be more spread. A cautionary point, and this again has nothing to do with clustering, but you are going to encounter this distribution. A cautionary point. If I make n prime smaller than 1, I can do that. Well, I would like to do it because this is a strength of a prior over thetas, and maybe I want to make a prior as weak as possible. Be careful, because if n prime goes below 1, between 1 and 0, the distribution, so for n prime equal 1, the distribution is uniform. It's flat. But if n prime goes below 1, something really interesting happens. The mass starts concentrating at the points. So basically, from a maximum, this becomes a minimum. And so the distribution changes shape and becomes concave. So many people have tried to put a really weak prior on their parameters by making this n prime small, and they got a very strong prior that the distribution is concentrated in one of the peaks. Remember that. So this is an example of the simplest distribution over distributions. Now, we'll go to the Dirichlet process mixture. OK. And the Dirichlet process mixture is another distribution over distributions. So the way I'm going, it can be derived in many ways. So just like the EM algorithm can be explained in many ways or derived in many ways, the Dirichlet process mixture is another model for clustering that has many ways to, many paths that get to it. The one I'm going to describe it is called the Poya-Orn. And it can be thought of a generalization of the mixtures of K Gaussians to an infinite number of Gaussians. Of course, in any real data set, I'm not going to have an infinite number of clusters. I'm going to just have as many clusters as the data supports or if the data requires. In that sense, it's infinite. I don't put any bound on K. And it's a Bayesian framework in the sense that now I'm not going to do maximum likelihood. I'm going to have a prior, which will be an extension of the Dirichlet prior that I've shown. So I'm going to start by some notation. I'm denoting theta k the parameters of cluster K, and assume the clusters are Gaussian, as many as I need again. And I'm going to now construct a prior over the clusters. So each cluster is a Gaussian distribution. I'm going to construct a prior over the Gaussian distribution, and that's the G0. And the idea is that whenever I need a new cluster, I'm going to draw from that prior. Okay. And then I'm going to need another parameter to tell me, which will be about the granularity. How many times do I need a new cluster? Or how many times should how often should I force points to fall in the same cluster at existing points? And that's alpha. That gives me the granularity. The larger the alpha, the more cluster I will have. In a funny way, you can think of this prior G0 as the mean of the distribution. Because if I draw a cluster with no data, it will fall. It will be described by G0. And you can think of alpha as the inverse variance of the distribution. And yes, it's a very flexible model. So in more detail now, suppose we have, we want to describe how our data were generated. When we talk about a finite mixture, the assumption is that whatever generated the data picked a cluster at random and then generated the data from the Gaussian corresponding to that cluster. Here we have a similar model. Except that now we are going to generate from another, the cluster from another process. And by the way, process means just a way of generating data, not necessarily IID, not necessarily independent. So it will look like, you'll see that the points here are not generated independently. So when I want to generate a new point, I do the following. First, I sample the Gaussian. And I sample the Gaussian by this formula. This is also called the Chinese restaurant process, CRP. So the new cluster, the cluster for point I will be an existing cluster with a probability that depends on the sizes of the previous cluster. So nks are the sizes of the clusters that already exist. At this point, I pick the new cluster with the probability proportional to the sizes. So larger clusters get a better chance of getting this point. And if these things wouldn't sum to 1, these things would sum to 1 if I wouldn't have this alpha minus 1 in the denominator. But I need this because I need a little probability mass to generate a new cluster, and this is proportional to alpha. I'm not sure if that minus 1, there may be an alpha minus 1 at the top. So basically, the normalization constant is whatever makes this sum to 1. This probability is sum to 1. So with probability alpha, I put the point in a new cluster. With probability mass proportional to the cluster sizes, I put it in an existing cluster. And this is the sort of one of the get richer processes where the larger clusters grow. But the larger the alpha, the more likely it is to create a new cluster. So you see how the coarseness of the clustering comes in by alpha. OK, and after I choose the cluster, if I'm in an old cluster that already has a parameter, a set of parameters, then I sample the point from that particular Gaussian. If I have chosen to create a new cluster, then I sample parameters for the new clusters from the prior, G0. And then after I get parameters for the new cluster, I sample my x, the coordinates of that point. So this is the last step. As I said, this is a process where the point n depends on the points prior to it, 1 to n minus 1. However, it can be shown, and this is not a simple proof, that the process is interchangeable in the sense that if you give me a set of data and this distribution, the probability of the data doesn't depend on the likelihood of the data doesn't depend in the order in which I present the x's. In the end, I will always get the same probability. And that's meant by interchangeability. Okay. Now, as I said before, in the case of the Gaussian, that I talked about, I have a spread of the centers, that's sigma 0, and I have an alpha that controls the granularity. As you see, if I have some belief that the cluster centers should be somewhere, then I should put the mean of G0 there, and I should put the sigma to be according to my spread. If I have no idea where the cluster centers should be, I should just take a large sigma for the prior over the clusters, over the Gaussians. And that has nothing to do with alpha, which describes the granularity. So I can choose them independently. In the general case, I'm going to assume that these f's could be something else than Gaussians. Yeah?
So when you said interchangeable, you said also that they're not IID, right?
Right. The process is not IID.
How do you show the interchangeability without assuming IID?
It's a proof. It's not trivial. It's not trivial. You can't see it. That's why I had to tell you. Yes. So basically, you can show that if you change the order of the points, you are going to get the same likelihood in the end. And probably induction has to do with it, because it has to be true for any n. Yes?
On the previous slide, when you sampled a new Gaussian mean, it was centered at 0. Are you assuming the data is?
So I sample it from another distribution, and I can assume that the centers are Gaussian. So I have a distribution over Gaussian parameters. And so a natural thing to say, that's a Gaussian. And I could set it at 0. I could set it at the mean of the data. That is the prior. So it's sort of, I set it to my belief, to my best belief. I would set it to the mean of the data. Or I would set the data to, I would center the data to 0 before I do this. Yeah? Yes?
So interchangeable is the same thing as exchangeable, right? It's also
yes.
Exchangeable.
Yes. OK. So in the general case, I can have any family of distributions. They depend on a parameter theta, which means that the prior is a prior over parameters. Yeah? So they are parametric distributions. Okay? And beta is some parameter that defines the spread of the distribution. If you know what conjugate priors are, how many of you do? Okay. Then it is convenient from the computational point of view to choose a conjugate prior G0 to the family F. Yeah? For instance, for the mean of the Gaussian, the conjugate prior is the Gaussian. For the variance of the Gaussian, the conjugate prior is the Wishart distribution. And the Dirichlet distribution that I've shown before is the conjugate prior for the multinomial. OK. Then, of course, the sampling of the clusters doesn't change. X is sampled from F's. And so I'm going to call alpha and beta the hyperparameters of the model. So it has two hyperparameters if I don't take into account this G0, which is also a parameter, but it's a function parameter. So this is the sampling model. This is what I assume. What you have probably already noticed is that because of this rich get richer phenomenon, larger clusters get more points, the distribution over cluster sizes will not be uniform. I'm going to have a few large clusters that have grabbed a lot of points and have grown very large, and I'm going to have a bunch of small clusters of different sizes. And that's one phenomenon. And they are described what's called the stick breaking process, which is another way of describing if you've seen it, it's another way of describing how the Dirichlet process mixtures are generated. Another thing that will happen is that the more points you sample, the more clusters you have. So the number of clusters is not bounded. If the number of points grows to infinity, the number of clusters will grow too. But it's growing slowly, and it's growing approximately like logarithm of it. So I will have a logarithmic number of clusters, and of course many of them will be singletons. So it's a great process to model outliers. And of course the rate of growth is governed by alpha. That's kind of obvious. So this is a generative model. But now we have data, and the question is how do we fit a model like this to the data, and how we get a clustering out of it. Actually, it's clear how we get the clustering. The question is how we fit the model to the data. So this is what I formulated as the clustering problem. I am given the priors, like the parametric family, the parameters of the Dirichlet mixture model, and I'm given the data, and I want to find the clustering. Now, if I have a clustering, just like for the EM algorithm, if I am given a clustering, then I can estimate the thetas in a Bayesian way, and we'll see how. And the other way around, if I'm given a theta for each parameter, that tells me which cluster it is, because I can see which cluster has that theta parameter. Of course, this is a way of writing concisely on a slide. In practice, when I implement this model, I'm not going to keep a set of parameters for each point. I'm going to keep a cluster label. Yes, but it's convenient to just keep a theta for each point, at least conceptually, which is the cluster a distinct cluster label. Okay. Well, it turns out that for this model we don't have an EM algorithm. We cannot estimate the parameters in closed form. Second, when this model was defined, and the great advantage of having a prior over functions, having a prior over clusters, is to work in a Bayesian framework. Bayesian framework is a paradigm for estimation. Just like maximum likelihood is a paradigm for estimation, Bayesian is another paradigm. And in the Bayesian framework, one never estimates parameters, at least not in theory. In practice, we always end with estimating parameters in the end, or very often end with estimating parameters. But in theory, we don't estimate parameters. In theory, we estimate a distribution over parameters. So conceptually, after I give you the prior over theta and the data, the result of the estimation will be another distribution G that will be the generative process together with the rest, will be the generative process for this data, for something that would generate data like this. Of course, that distribution can be represented in closed form. Yes?
Sorry, I think I missed where you got beta. Alpha, we explained, we talked about beta. I'm not sure.
Beta is a parameter of this distribution over clusters. How alike I want the clusters to be before I see any data. So the clusters will depend on the data, but am I going to force them to look the same? So am I going to pull the centers together? Or am I going to let them be where the data is?
So is that some kind of variance on the distribution?
It's a prior of where the Gaussians are going to be, and it's a prior on how big the initial variance of the Gaussians are. Yes? And that's important because suppose I create a new cluster. I have just one point in that cluster. I can't estimate its variance from one point. So then I will going to use whatever this G0 tells me about the variance of a cluster, and as a prior, and with one data point, I'm going to estimate the posterior distribution of that Gaussian, which usually will shrink the Gaussian a little, typically, because I see some data. Yes?
Are there any constraints on G0 in that?
G0 has to be a distribution over Fs. Yes? And again, it's convenient to use, for computational reasons, it's convenient to use conjugate priors, because then you can do computation in closed form. But otherwise, no, it's what I believe represents the data. Yeah? So if I believe that clusters are Gaussians, I put F to be Gaussians. If I have discrete data, then F will be a multinomial.
Okay, so through the Dirichlet process,
Yes, this form of sampling, this having a distribution over functions, sampled in this way. Yeah, that's the Dirichlet process. Okay. Okay, so again, I start with a distribution, and if I sample from it without any data, I get some clusters sampled around 0 with different points in them. But now I have data. And so if I do go through this Markov chain Monte Carlo estimation, I'm going to get another distribution that will, if I consider it a distribution, will generate data that look like my points. The purpose, however, is not in clustering is not to generate new data, but to actually get the parameters that describe my points well. And group the parameter, the clusters in, group the points into clusters. Yeah, that's the purpose. But I could do in the Bayesian framework. I could do more. I get a whole distribution, just like when I estimate a mixture of k Gaussians. I can sample more data from the Gaussians because I have a probabilistic model, and that's in addition to having clustered the data. Here too, the goal of what the estimation will give me will be a new distribution G that will generate data like the one I have, like the data I have. Yeah. In that sense, it's a very powerful framework. It's getting us more than we are asking for. However, computationally, we have a problem because we can't. These distributions don't have a closed form expression, or have a closed form expression that is not computable. It's just an expression of, it's a probabilistic model, and therefore the estimation has to be done by Markov chain Monte Carlo, which means that I'm going to change start with some parameters and change them a little bit around, sample around until I get to a region of the space where I have high probability, where the models have high posterior. So I start with an initial configuration and I change it. And how many of you know what Markov chain Monte Carlo is? Because I don't have. OK, so you do know what it is. Yeah. So essentially, in Markov chain Monte Carlo, at every step, I jump from one state. And one state is a clustering plus some parameters. So it's a pretty complex state. I jump from one state to the next state in a way that ensures that if I take independent sample from this random walk in the state space, I am going to match a certain distribution that I want to match. In this particular case, the distribution that I want to match is the posterior, is the G that's obtained after I observe the data and I have with a given prior. And so if I do a lot of Markov chain Monte Carlo steps, and then I pick a state at random, it will be a state of high probability. With high probability, it will be a state of high probability from that posterior. And I also hope that these states with high probability will be the same. I'll get back to it after I explain the algorithm, because this is a bit too abstract now. So concretely, what do I do? This particular algorithm, it's not the only algorithm that exists. It's one that's easier to put on a slide and natural to explain as a first step. Looks like EM in the sense that it alternates between cluster assignments and parameter estimation. Yeah. OK. So the cluster assignments. I have started from an initial state, so every point has a cluster, and every cluster has some parameters at the beginning. But I can just assume that, yeah, so every point has some parameters. Every cluster has some parameters at the beginning. And now I pick a new point, and I take it out from the cluster where it was. So the new nks that you'll see here take into account that I've taken out the point. So they sum to n minus 1. Yeah. That's not written here. So I pick a point, and then I sample it in a way, I assign it to a cluster in a way that's very similar to what you saw before. But now the clusters have data. So when I put it into an old cluster, I put it by how well the cluster predicts my point, which is its likelihood, this f given theta k, multiplied by the size of the cluster, which is the prior. Larger clusters get priority. Yeah. And if I'm going to try to put it in a new cluster, I'm going to weight it by this integral, which is how well the prior describes my point. The G0 describes, the integral over all functions describes my point, which is the probability of my point being likely in a new cluster before I have seen actually what F5 given. Yeah? That's because the clusters already contain data. And this is assignment. And I roll through this for all the points, which means that many times a point will be assigned to the cluster where it belonged if that cluster describes it well and is large enough. But occasionally, any cluster, even if it's described, any point, even if it's described well by a cluster, can jump to another cluster or create a new cluster. So it's a random process. Okay? And then if I actually create a new cluster, I have to get some parameters for it. And the parameters are not directly from the prior, are from the prior multiplied with the point. So are from the posterior of the thetas given the point. And that's the assignment step. Then the next step is getting new cluster parameters. But because I'm doing Bayesian estimation, I don't want to just get a value for the parameter. I would like to get a distribution for the parameters. And that distribution is represented by actually getting a sample from it. If I could represent the distribution in closed form at this point, I would. But I can't. So the best we do is get a sample. And that's done by collecting all the points that are in a cluster and sampling the parameters according to the likelihood times the prior, which is the posterior. Yeah? Yes?
Is there a normalization constant?
Yes, there is a wherever you see an alpha, there is a normalization constant. Yeah? And here too. So these are, well, OK. So here and in all of Dirichlet process mixtures, I'm going to heavily use the fact that yeah, that's a fundamental relation in statistics. That's behind all this. And again, likelihood is how the model predicts the data, and prior is this prior over functions, for instance. Yeah. Yes? And so this is one step of Markov chain Monte Carlo. Moves me from one state to the next state. Now, if I iterate this many times, Markov chains tend to mix, so that they tend to forget the initial state and to migrate towards parts of the state space where they have high probability, which means that after many iterations, and it's a question how many, it's a question always in Markov chain Monte Carlo, I'm going to get to a state that, to a distribution that doesn't have to do with the starting point. It's what's called the stationary distribution of this chain. And that stationary distribution with high probability stays in highly probable states. So if I look at the current sample, I'm going to see something that's likely in the posterior. And if I take the next sample, I'm going to get another clustering and different parameters, but they will not be so very different. In fact, they will be quite similar. And this is the philosophy of Dirichlet process mixtures estimation. Let's see if there are more questions. Yes?
How do you estimate the hyperparameters, alpha and beta?
I don't. They are given. They are my belief. This is how I believe. So alpha is the smoothing parameter, how granular I want the clustering to be. Of course, if you want to be Bayesian to the end, people can put a prior on those and then sample from that too. So if you really don't know them and you want to estimate them, you can put a prior and do the same sampling for everything. You'll need a lot of data. Like the more parameters you sample, the more data you need to actually believe them. But what happens, one thing about hyperparameters is that they can be drowned by the data. In particular, if you put a mixture of 3 Gaussians through here, for most alphas, you're going to get 3 Gaussians plus some outliers, maybe. Yes, there are other questions. Yes?
Would it make sense to do the iterate step several times instead of just once? To get a better sample?
Oh, iterate what, this step?
The first step. So this is the step where you're taking a step to the grid space, right?
Yes. So I I don't know. Because if I iterate this step, so the question is, what if I iterate this step several times? I think I would be sampling from the same distribution. So unless I actually keep them all and sort of do something with the ensemble, they would be pretty much equivalent. Like the next one wouldn't be better than the previous one. And that's true for here too. One sample is one sample, and if the distribution is concentrated, then they will be representative samples, and if it's not, it's a problem. Yes?
So if G0 is not conjugate, do you have to use like metropolis or something?
If G0 is not conjugate, then the question is, how do I sample from this? And that, of course, depends on G0 and F. And I would really like to have a closed form. I would really like to have an efficient algorithm for sampling from there, because I have to repeat this many times. But if I don't, then there are sampling procedures from getting a sample from this. So you can do another Monte Carlo algorithm just to get a sample of theta. And people actually do it occasionally. If the prior is conjugate, very often there is also an algorithm for sampling from it. So Gaussian with Wishart, you get you call a function and you get a sample. Yeah?
Would it make sense to, instead of doing a hard assignment to a theta case, to keep that posterior around, and then when you're sampling for the existing K, integrate over the...
Yeah, I would love to keep the posterior around, but I can't because it doesn't have a functional form. Or I would have to sort of go back and integrate there. So, but yes, it would be really nice if I could keep the posterior around. In fact, if you can keep the posterior around, you can eliminate this step sometimes. And sometimes this step. So yes, if things fall in closed form, you can eliminate some of these steps, and that's faster. So you really want to do that. But it's not always possible. Yes?
I guess it's kind of high level. So why is this called the distribution mixture? Because we don't even have to use the distribution parameter.
Oh, I said before, this is because it's a generalization of that prior over functions with this sampling process. OK, so this is just one algorithm. And all your questions were very good about how to make it faster, how to sort of get it to work when I have my specific priors. This is actually a very active area of research because the same principle applies to other things than clustering. For instance, if you probably know that clustering is a process with a hidden variable, the cluster variable is not seen. So if you do finite mixtures like EM, you are estimating the hidden variable, which is the cluster label. In this case, the hidden variable is the cluster label in this space with an arbitrary number of clusters. You can generalize this to other processes that have hidden variables that are more complicated than clustering. Also, it's an active area of research in particular for mixture, how to make this algorithm run faster. And there are issues like the ones you raised, how to do this sampling faster, how to do this sampling faster. Anytime you can do an integral in closed form, that makes things faster. But there are also the high-level issues. How many steps of the Markov chain random walk, Markov chain MCMC, do I have to take before I have converged to a place that's independent of the original state? And that has to do with something that's called the mixing of the Markov chain. So how fast do I forget the past? How large a jump can I take? And from this point of view, this algorithm is not so great. The reason is that I change the point assignments one at a time. So if there is a really big cluster, suppose I have a mixture. Like suppose the data comes from a mixture of 3 Gaussians, but I don't know it. And 2 of the clusters are merged. Then, because I have 2 clusters merged, I have a large variance. And the large variance means it can explain points far away and tends to grab points far away unless another cluster likes them very much. And with EM, I'm going to just try another initialization and maybe split them. With this, I have to split them by moving points from the large cluster to another, starting a third cluster. and make it grow and grab points. Well, that's very hard because every point decides to move kind of on its own. And so it's very hard to start taking points out of another cluster that's large and creating another large cluster. And so this tends to get stuck in this fashion and take a long time to decide where to go. We say initialization doesn't count, but there are points in the state space from which you mix faster and points in the state space from which you mix slower. So the general wisdom when you start this process is don't put all the points in the same cluster, which is the nicest and simplest thing, because it will be very hard to split. The wisdom is put every point in its own cluster, because then they're starting to find each other and merge. And that happens actually quite quickly. Like if you start with every point in the same cluster, the number of clusters after the first step decreases very fast. It's much smaller. So they do that. And people have worked on algorithms that split and merge. Of course, if you split clusters, you can have to have a step to merge. And there is some mathematics involved on how to do it correctly to make sure that you are sampling from the correct posterior. However, that's still an active area of research. Good splitting algorithms, merging is simple. You know who goes where. But good splitting algorithms are still wanted. OK. So with this, I have pretty much finished with Dirichlet process mixtures. And I'm going to summarize in the next, I'm going to take a few more minutes from you to summarize parametric clustering. In fact, let me see if you have more questions first about Dirichlet process mixtures. All right, then let's remember the differences between parametric and non-parametric. In parametric clusterings, I always have a cost. Sometimes it's a likelihood. Usually my cost is hard to optimize, so I have to do, it's a challenging problem to optimize it, and it's an active area of research whenever the cost is any good. I'm always usually assuming that I know something about the cluster shapes. And as you will see, this is true, as you have already seen, this is also true for Dirichlet process mixtures. Like, for instance, that they are Gaussian, or in k-means that they are round. And it is required to know k, and then there is a sort of a wrapper algorithm, so an outer loop of finding k. And that's, again, active research, because we really don't know how to find k optimally, unless our model really fits the data. Also, technically, it gets harder with large k in the sense that the optimization problem is harder, mainly because the optimization problem is harder. And for all I said that it's hard to, there are so many open problems in parametric clustering, non-parametric clustering is even harder to study. So we have even fewer results about what is true in the clustering sense. By contrast, the biggest difference between non-parametric and parametric is that if I work with density-based methods, I do not have to assume any shape for the clusters. The clusters can have any shape, any possible shape. Whatever the high regions of the density are, that's the shape of the clusters. Also, another difference that I've already stressed enough is that I do not have to prescribe the size of the clusters, but the number of the clusters, but more the granularity, how easy it is to points to split and form a new cluster. And of course, that's extremely good and extremely useful when I have outliers. The downside is that they take more work to fit. They are all computationally intensive, all of them. And moreover, to make things worse, they are recommended when I have lots of data. For statistical reasons, because non-parametric, any non-parametric estimation converges to a slower rate than 1 over square root of n, which is the rate of parametric models, technically. Yes. Also, because they are more useful when I have more data. That's when I really want to get more information from the data that the non-parametric framework lets me get. So there's this cautionary or this conflict between I want to use them for lots of data, and that's when they are slow. However, there is, I already talked about algorithms to make this fast. This is an active area of research, and a lot, like, you don't have to be naive. If you really want to fit large data sets with non-parametric models, there is software out there, and if you work at it and are intelligent, you can do it. It's possible. There's another slide about when to use what, but I'll keep it for after the break. Yes?
Are there any like hierarchical models where you can try to infer better alpha so that you can infer the granularity from the data instead of because otherwise you're kind of academic J sort of.
OK, so the question is, are there any hierarchical models? Yes, actually, for almost any of these clustering methods, there is a hierarchical variant. There are hierarchical Dirichlet process mixtures. And you have seen cluster trees that are hierarchical clusterings of sort of density-based clusterings. And there are hierarchical models for standard mixtures. And so basically, for almost any cost function, you can have a hierarchical model and a hierarchical algorithm. Yes. Yes, there are hierarchical models also for Dirichlet process mixtures. There is a problem when you have a hierarchical model with hidden variables. You have to be careful, though, because sometimes the hidden variables are not identifiable, especially if it's a probabilistic model. If it's a hard clustering, it's simpler. But however, these have been solved. So people have worked on hierarchical models for the Dirichlet process. And if you Google them, you find them. Other questions? Yes?
How sensitive is the Dirichlet MCMC to alpha, to variations in alpha and beta?
You assume, as usual, that you have lots of data. And if you have lots of data, then only the outliers will be sensitive. Only the very small clusters will be sensitive to alpha, to beta. And so the question is, how sensitive is the model to the parameters? Typically, the more data you have, the data should drown the prior when you have more data. Okay? However, when you have very small clusters, they will be more sensitive. So if you have a strong prior that the clusters should be in some place, small clusters will go to that place because that's your prior. So you don't want to force them to be somewhere. Okay? And the granularity of the small clusters will depend on alpha. But the large clusters, no. So if you have large clusters on the data, you will get the large clusters. Thank you.
Make a quick announcement. Can you hear me? All right. We're trying to take a group picture at the end of the day today. Hopefully the weather will cooperate. In the worst case, we can do it inside. The reason I'm mentioning this, please don't disperse after the last moment. We'll try to have a group picture. Thanks. Oh, we're gonna depart